Now what we want to do is talk about heat pumps, and we could use, this is using refrigeration unit for both heating and air conditioning of your home. And so we'll briefly look at this. And basically, the refrigeration unit remains the same. It all depends on what your purpose is. So COP for heat would be equal to Q out over W net. COP for cooling, which we've been discussing, is Q in over W net. And the house requirements drive the size. House requirements determine the load. So they determine the load. So in the summertime, if I have my house, so here's the house, and what I have here is, if I do this for the summer, typically up here in the house you have your evaporator. So very often that's in the attic, or I won't say always, but that's the evaporator. And basically you have an air circulator goes over the evaporator, and cool air goes in the house. And outside is where you have your condenser. And there's obviously piping that relates to both. So the heat load in the summertime is you want to keep this cool. This is at a higher temperature, and so you have heat flow in. You have to remove that heat flow, and that's how this happens. So this is the summertime requirement. In the wintertime, you're using the same system, but they switch the valving. So they're similar in terms of what they look like, and they change the valving. So then in the winter, we have this be the condenser, and here's the evaporator. And so now, and then obviously the air handler in both cases, I have the airflow inside the house goes over this. But now in here, I have, this is creating warmth because heat's flowing out and I have to replace that heat. And so here's the evaporator. It's gaining the Q in at a low temperature, but then I'm just adding work to it and I get the boost in. So the units are the same, they change the valving, and so it's a nifty system in terms of that. What I thought I'd do is look at problem 1620 star. And in this, we have, it's R12 vapor compression. We have 48,000 BTUs per hour of heat needed. T inside, 70 degrees Fahrenheit. T outside is 30 degrees Fahrenheit. And we're going to introduce the idea of a pinch point, or the minimum temperature difference between the heat exchangers. And so minimum delta T for the heat exchangers is 20 degrees Fahrenheit. And so what this does is, so now I'll draw the vapor compression system. We're going to do an ideal one, and we'll see this introduces this idea of the minimum, and so this is sometimes called the pinch point. So if we have the condenser, evaporator, and the compressor. And we're just going to deal with an ideal system at this point, and we'll draw a TS diagram and see how this plays out. So if it's 30 degrees outside, so outside is 30 degrees. That means the temperature inside the evaporator has to be 10 degrees Fahrenheit. So this is going to be 10 degrees Fahrenheit. So I have to have a 20-degree temperature difference between the fluid inside the heat exchanger and the air outside the heat exchanger. Similarly, if the inside air temperature here, if this is 70 degrees Fahrenheit is the temperature here, then the condenser has to be at 90 degrees. So that establishes the pressure requirements for this. So we have a condenser, sat temp is 90 degrees Fahrenheit, and the evaporator is 10 degrees Fahrenheit. And so that establishes our units, and then I'll go through and look up the enthalpies and do the calculations. So H4 is equal to H sub F at 90 degrees Fahrenheit is equal to 28.71. H1 is equal to H4. H2 is equal to H sub G at 10 degrees Fahrenheit is equal to 78.33. S2 is 0.168. S3 is equal to S2. H3 is equal to 88.66. And so now we have the enthalpies around this cycle. And this is for an ideal vapor compression system. Obviously, all the actual aspects of subcooling, superheating, etc. come into play. And so now Q dot out is equal to the mass flow rate times H4 minus H3. So the heat out that I want for heating comes out of here. And so I know this is minus 48,000 because it's out, the minus sign, is the mass flow rate times the difference in this, 28.71 minus 88.666. And so I have that the mass flow rate is equal to 800.7 pounds mass per hour, which is equal to 13.34 pounds mass per minute. And the power, W dot net, so now I'm doing the first law on the compressor, is equal to the mass flow rate times H2 minus H3. So this is equal to 13.34 times 78.33 minus 88.66. I have that the power, let's see, the power is equal to minus 137.8 BTUs per minute. And that's equal to 3.25 horsepower. And there are 42.4 BTUs per minute per horsepower. In the COP for heating, is equal to Q dot out over W dot net. So COPH is equal to 48,000 divided by 60 to give it in BTUs per minute. So I converted this to BTUs per minute divided by 137.8 8. And so the COP is 5.8. So that gives us the COP for heating for our heat pump. And for homework, so you can do a couple of these also. We have 16, 19 star, and 16, 21 star.